Hi again, welcome to the first of the network videos dealing with trees and spanning trees. Here we discuss the paths along which we can move through a network and visit every vertex, that is, to span every vertex. In the next video we extend that technique to finding minimum spanning trees. In the previous videos we established the concept of a network being a set of lines or edges linking stages or activities, that is the vertices, in some way. And networks can be viewed in many different ways according to their structures. We've looked at walks, trails and circuits, paths and cycles, whether the networks are connected or unconnected, whether they're directed or undirected, or whether they're Eulian, etc., etc. Examining a network in terms of the path between the two vertices, we say that if there is one and only one path between each pair of vertices, then we have a tree. Hence we're going to have an undirected graph. It's got to be connected and there can't be any cycles. In this diagram we have a network. It doesn't have any arrows on the edges, so it's an undirected graph. It connects all of the vertices together and there are no cycles, so therefore it must be a tree. In this diagram we have four edges flowing away from a central vertex. So there are no arrowheads, so it's an undirected graph. All the vertices are connected and there are no cycles, so the diagram shows a tree. In the third diagram, all the three properties exist and apply, and so therefore that's the third of our trees. In the next diagram we have a network made up of two separate parts. There is no link or edge between the two parts, so it's not a connected network, so therefore that's not a tree. In the final diagram we have a network which is undirected graphs. It's connected but it has a big cycle, so not a tree. In each of these trees we have edges which don't connect to other edges, and they're called leaves. So the leaf is the end of a branch in a network. So here we have an indication of some of the leaves in those three diagrams. Now let's have a look at the three diagrams from another perspective. In the first one we have four edges and we have 5 vertices. In the second one we have 4 edges and 5 vertices again. In the third diagram we have 9 edges and 10 vertices. So in a tree there is always one more vertex than the number of edges. Not a bad little relationship to remember, particularly when we come into the next video. In any given network, a number of different trees can be identified. What we've got to make sure is that all the vertices are connected and that we don't create any cycles. So we'll take away our graph and just leave a picture of our vertices there, and we're going to start at vertex G. From G we can go to F, from F to A to B to D, and from D to C. We have included all of our vertices. We haven't created a cycle, so therefore we can say that the path GF, AB, DC is a spanning tree. If we included an edge from D to F and linked those two vertices, then a cycle would be created, and then the walk through the network is no longer a tree. So we'll get rid of that green diagram and try something else so that DF is not offended at being left out of the previous one. So now we can go from D to F to A to B to C to G. We've got all vertices connected. There's no cycle being created, so therefore DF, AB, CG is another spanning tree within the same network as we started off with. So we've now got at least 2 spanning trees within the original network. Usually the edges in a network diagram have weights, and these weights written along each edge indicate to us the time to complete each activity, or maybe the cost to complete each activity, or the distance between locations. So AB edge has a weighting of 2, and that might be that it's going to take 2 days to complete the activity that's going to be required from A to B, or it might be that the cost of that is $2 million, or the distance between A and B is 2 kilometres. To compare alternative spanning trees from one network, we add the weights along each path. So if A, B, D, E, F, C is one possible spanning path here, then the weight from A to B is 2, the weight from B to D is 1, from D to E it's 3, from E to F it's 2, and F to C is 2. So we add up all those numbers and we find that the weight for this particular path is 10. Now instead of that spanning tree, we try another one. From A to D to D to E to E to F, F to C, C to B. So we write down all of those weights, AD being 4, DE being 3 and so forth. We add up all of those for this spanning tree and we have 15. So the weight of this tree is 15. If the weights were describing time, then clearly the first path would be quicker to take than the second path. So in summary, a tree is a network having one and only one path between each pair of vertices. A spanning tree is a tree that links all vertices in a network without creating any cycle. And the total weight of a spanning tree is the sum of the weights of each edge. So in the next video we will learn 2 common ways to identify spanning trees with minimum weights. Consolidate what you've learnt here by doing the test yourself questions on the website drjaysmaths.com. Hit the like button and subscribe if you haven't already, because if you do, then you get notifications about new videos. Good luck. See you in a spanning tree soon.